Hi, Math 206. This is Dr. McGathy, and we're entering the last section of the semester, which is our unit on volume. So first of all, volume is a three-dimensional type of measurement. So take a minute, pause the video, and just brainstorm some units that you use to measure three-dimensional objects. So pause the video. All right, some typical three-dimensional units for measure include like cubic feet, cubic inches, cubic centimeters. So basically any one of our one-dimensional measurements, if you take the cube with side lengths, those 1 unit each of those measurements, you'll get a three-dimensional measure. But we also have some measurements that are that don't have a one-dimensional analog, such as gallons. That's a three-dimensional measurement for measuring volumes. Fluid ounces. And milliliters or liters. And this would be our metric system unit, base unit would be liters. So then you've got milliliters, centiliters, deciliters, and so on. All right, so these are just some typical measurements. And let's calculate some volumes here. And you'll see these types of questions are typical for the elementary school ages, because you have to account for some of the cubes that you don't see that are hidden behind the object. So let's go ahead and find the volume of each one of these figures and calculate the surface area. You can go ahead and pause the video and then restart it when you're ready. So the volume of this object would be 1, 2, 3, 4, 5, 6. That's the first layer. 7, 8, 9. So there are 9 cubic units here. Would be the volume. And over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, we also have 9 cubic units for the volume. But now we're being asked to compare the surface area. And the first thing you would typically do is ask, do you have any conjectures, any thoughts about the surface area? Do you think they have the same, these two objects have the same volume? Do you think they have the same surface area? All we did was move this blue block from this position over 1 unit to get this object here. So obviously they have the same volume, but do you think that the surface area changed? So let's go ahead and calculate that. I've got 1, 2, 3, 4, 5 to be the surface that's exposed on the left. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. The surface area here would be 26 units for everything that is showing here. And on the bottom, you'd have 1, 2, 3, 4, 5, 6. So 26 plus 6 would be 32. And that would be square units. All right, so over here you'd have actually almost exactly the same surface area, because almost all of the same surfaces are exposed. The only thing that's different by moving this blue cube to the right 1 unit is that you've exposed a few more surfaces, namely the right-hand side of this red cube and the left-hand side of this blue cube. And then, well, this cube here is covered by the block, but now this one is exposed. So those guys kind of cancel each other out. Anyway, so we end up with 2 additional units. So the surface area here would be 34 square units. So these are some explorations that you might do with your students when you're considering volume and comparing that to surface area of your objects. All right, so we're going to develop some formulas and also discuss conversions between units of measure. So first, let's discuss volume of prisms and cylinders. Before we develop our formula, I want to discuss how we know that the formula for a prism will work whether you have a right prism or whether your prism is angled or whether the prism actually, the sides are not straight. So this is what is called Cavalari's principle. Cavalieri was a mathematician in the 16th, 17th century, and he discovered that the volume of a right prism will be the same as the volume of an oblique prism with the same base and the same height. And you can imagine that by imagining a stack of pancakes, right? And the stack of pancakes has the same volume whether you stack your pancakes exactly perfectly one on top of each other so that the stack kind of makes a 90-degree angle with the ground, or whether you push the pancakes over and let them like lean over a little bit. You still have the exact same volume, whether or not your stack is straight or if it's leaning. All right, so to develop the formula for volume, what we'll do is imagine that your three-dimensional shape is actually just stacks of your one-dimensional shape. And it's a stack each unit high. So for each unit, the volume is just 1 unit high of whatever area you have on your base. So then if you have each of these stacks right on top of each other, then your volume will be h groups of the area of your base, which in this case would be length times width. So length times width times height is like how we normally see it. So this would be for a rectangular prism. For a rectangular prism. For any other object, be it a prism or a cylinder, the volume would be h times the area of whatever your base is. So if you have a cylinder and your base is a circle, it would be 2 pi r times h. Let's see how that works in these examples. Let's find the volume of this cube. The cube has side length 6 centimeters. So since it's a cube, all the side lengths are the same. So the volume of this cube would be 6 times 6, which is the area of your base, times 6 units high. And 6 times 6 times 6 gives me 216. And now my units will be centimeters cubed. So cubic centimeters. So you imagine, again, that you've got 1, 2, 3, 6 layers high. And in each one of these layers, you've got 36 cubes on the first layer, 36 cubes on the second layer, all the way up to 6 layers. All right, so to find the volume of this right rectangular prism, you would do 3 times 10 to get the area of the base, and then times 15. And whatever this is, your units will be cubic centimeters. So 3 times 10 times 15 would be 450 cubic centimeters. So again, what you imagine is having 30 units on one layer of this prism, and then you've got 15 layers, so 15 groups of 30. Or using the associative property, you can think that you have 15 times 3, which is 45 cubes on the, stacked up on top of each other, and And then you've got 10 layers deep of those. All right, let's look at the right circular cylinder. So again, here to do the volume, we'll do the area of the base, which is pi r squared. So pi times 5 squared times the height, which is 10. And whatever this is, the units will be cubic centimeters. So 5 squared, 25 times that, 250 pi cubic centimeters. And of course, mathematicians prefer using the symbol pi because it's exact, but if you were going to purchase some liquid to fill this cylinder, you would probably say it's like approximately 250 times 3.14 or 785 cubic centimeters. All right, and for our last formulas, we want to compare pyramids and cones to prisms and cylinders. So it turns out that a pyramid and the prism with the same base and the same height, you can fit 3 of these pyramids precisely inside the corresponding prism. Same thing with cylinders. You can fit exactly 3 cylinders with the same base and height inside, 3 cones with the same base and height inside one cylinder. So it turns out that the volume of a pyramid would be 1/3 the volume of the prism, which is the area of the base times the height. And same thing here for the cone. The volume of a cone would be exactly 1/3 the area of the base, which is pi r squared, times the height, which is h. All right, so let's see how that works in this example. Consider this pyramid. Your base, so the volume here will be 1/3 the area of the base, which is 4 times 4, or 16 square centimeters, times the height, which is 5 centimeters. So all of this would be in terms of cubic centimeters. So we would do 1/3 times 16 times 15, which gives us 80 cubic centimeters would be the volume of this pyramid. Let's do the same thing for this cone. The volume of this cone would be 1/3 pi r squared, so r is 6, times h. Now here, I actually don't know what h is, but I do know the slant height is 10 centimeters. So in order to find the height of the cone, I'll use the Pythagorean theorem. A squared plus b squared equals c squared, where I'm thinking of the height of the cone, the radius of the cone, and the slant height as being the lengths of the sides there. So I'll use h for the one leg. H squared plus 6 squared equals the hypotenuse squared. So that is h squared plus 36 equals 100. Let's subtract 36 from both sides. We get h squared equals 64, where h is 8 centimeters. So it'll be 1/3 pi r squared times the height, which is 8. So I'll have to do 36 times 8 divided by 3, which would give me 96 pi cubic centimeters, which is approximately, by substituting 3.14 for pi, 301.44 cubic centimeters.